Hello! We're going to be looking at the ever-important relationship between enthalpy, entropy, and free energy. Specifically, we'll be looking at 4 different reactions, and we're going to be considering the enthalpy of the reaction, if it's endothermic or exothermic, and if it leads to an increase in entropy or a decrease in entropy, and we're going to see how that affects the sign of delta G. We're also going to be utilizing a graph to help us better visualize the temperature dependence of spontaneity of a reaction. Before we begin, let's take a few moments to get acquainted with the graph that we'll be utilizing to help us predict the qualitative relationship between enthalpy, entropy, and free energy. What we're doing here is we're plotting delta G, change in free energy on the y-axis, and temperature on the x-axis. Where the two of them meet, that's where both are equal to 0. So up here we've got positive free energy corresponding to a non-spontaneous reaction, and down here we've got negative free energy corresponding to a spontaneous reaction. It is important to note there are a lot of different ways that you can depict thermodynamics in graph form. Always make sure to look at your axes to see what exactly it is you're looking at. With that said, let's take a look at some examples. The first example that we're going to be looking at is a form of combustion. The most classic type of combustion that we look at in general chemistry is when we take a hydrocarbon, in this case propane, we react it with oxygen, we get carbon dioxide and water as products. It's important to recognize anytime you see a combustion reaction, you're looking at an exothermic reaction. So we know right off the bat the sign of delta H is negative. What about the entropy? Well, here we're going from 6 moles of gas to 7 moles of gas. Generally speaking, when you're going from fewer moles of gas to more moles of gas, you're looking at an increase in entropy. So our sign of delta S here is going to be positive. Now let's take this enthalpy and this entropy and see how it relates back to free energy delta G. In order to do that, first let's consider the extreme of about absolute 0. We're not going to deal with absolute 0 itself because everything will be kind of stuck in place. But 0.0000001 Kelvin, practically absolute 0. So on our graph over here, temperature at 0. At that temperature, we can see here that T delta S, if this is 0.000000001 Kelvin, that basically makes this whole term negligible here. So the free energy is just going to be reflective of the enthalpy. Since it's negative at about 0 Kelvin, we're just going to put a little mark here to show us that our free energy change would be negative at these very, very low temperatures. Then, as the temperature increases, what happens to delta G? Since delta S is positive, as the temperature increases, this number gets more and more positive. So we're subtracting an increasingly more positive number. As we do that, the free energy will get more and more negative. As we can see, in this particular combustion reaction, delta G is always going to be negative. There's no point where this crosses the x-axis. So reaction like this would be spontaneous at all temperatures. Our next example is actually another type of combustion. Here we're combusting hydrogen. This is also known as the balloon reaction because it's a department favorite. Anytime you have a hydrogen balloon go off, that's this reaction right here. So again, it's a form of combustion. We're taking hydrogen, we're reacting with oxygen, and we're making its oxide, water. So anytime we see combustion, we know it's a negative delta H. And you've probably seen this reaction before. It makes a fireball. That's an exothermic reaction. What about the delta S? Well, in this case, we're going from 3 moles of gas in the reactants to 2 moles of gas in the products. So we're making fewer moles of gas in the products. So we can see that the entropy change is going to be negative as well. What implications does that have on free energy, delta G? Well, let's look at our graph. So we can see here, once again, considering this is an exothermic reaction, if we're at around absolute 0, takes this whole thing out, because if this is basically 0, this whole thing's basically 0. So at really low temperatures, this will have a negative free energy change. What happens as the temperature increases? As the temperature increases, well, delta S is negative, so we're subtracting an increasingly more and more negative number. Since we're subtracting a more negative number, that means that delta G actually gets more positive as temperature increases. So this graph actually goes something like this. What does that mean? Well, we can see that at some point our line here crosses the x-axis. On this side, delta G is negative. That means up until a certain temperature, we would need actual numbers in order to figure out what the temperature is. Up until a certain temperature, this reaction is going to be spontaneous. But then after we exceed that temperature, after it gets too hot, actually this will be a non-spontaneous reaction. Our next reaction is the decomposition of limestone, or calcium carbonate. In this reaction, we can see that heat is listed as a reactant. What's that there for? That's just there to give us a cue to let us know that this is an endothermic reaction. We have to put heat into it to get it to go. So our sign of delta H is going to be positive. And we're going from a mole of solid to a mole of solid and a mole of gas. So we're producing more moles of products, and moreover, we're going from solid to gas. So we're looking at an increase in entropy. So we've got a positive delta H and a positive delta S. What implications does it have on the free energy? Well, if we go over to our graph at 0, a temperature of 0, delta G would be just equivalent to our delta H, which is positive. So I'm just going to put that up here. And then as the temperature increases, well, positive delta S, that means T delta S is going to get more positive, which means we're subtracting a more positive number, which means our delta G is going to drop with temperature. So as temperature increases, this will go further and further down. And at some point, it will cross the x-axis. Again, what's the implication of crossing the x-axis? Well, that means that's going to be our temperature where the reaction goes from spontaneous to non-spontaneous, or in this case, from non-spontaneous to spontaneous. So here we've got a positive delta G. Past here we've got a negative delta G, so it's going to be non-spontaneous at low temperatures and spontaneous at high temperatures. One more example. The last reaction that we're going to look at may look a little bit familiar. It's actually the same reaction that we looked at for combustion of propane, except reversed. So what we're doing here is we're taking carbon dioxide and water, using it to make propane and oxygen. It's the reverse reaction of the combustion that we looked at before. So what does that mean about the enthalpy? Well, since this reaction is the reverse of combustion, we're forming the hydrocarbon and oxygen from the CO2 in the water. That means that it must be an endothermic reaction, because the reverse of an exothermic reaction is an endothermic reaction. How about the entropy change? We're going from 7 moles of gas to 6 moles of gas. So we're making fewer moles of gas, which means that we're looking at a negative entropy change. Now then, let's see what implications this has on the free energy. So at absolute 0, where this whole T delta S term doesn't make a difference, delta G would be equal to delta H, which is positive. So I'm just going to put a mark here. And then as the temperature increases, this gets more and more negative. And as we're subtracting a more negative number, that means that delta G is going to get increasingly more positive as the temperature goes up. What does that mean about the spontaneity of this reaction? Well, we can see there's never going to be any point where this can cross the x-axis and become a negative value. So a reaction like this that has a positive value for the enthalpy, endothermic, and a negative value for the entropy, it's going to be non-spontaneous at all temperatures. And that concludes our 4 different examples. We looked at, in fact, all 4 different thermodynamic situations. We looked at endothermic and exothermic with an increase in entropy or a decrease in entropy for both. Thank you very much for your time. Have a great day.